Section 5.2 is the characteristic equation. So this is our tool to find eigenvalues. All right, so let's have a look at what we've got in the definition. First, we have an n by n matrix A, the polynomial P of lambda, in other words, a polynomial with lambda as the variable, which is defined by the determinant of A minus lambda I as a single matrix, where we have lambda as some unknown times the identity matrix. It's called the characteristic polynomial of A. So this is our characteristic polynomial. And the equation, P of lambda, when we set this polynomial equal to 0, it's called the characteristic equation of A. So that's this polynomial and the characteristic polynomial and the characteristic equation. So why would we define such a thing? What's so useful about this characteristic polynomial and equation? Well, remember this: if we seek non-trivial solutions to this equation, a minus lambda I times x equals 0, the homogeneous equation for a minus lambda I, right? In order to find eigenvector eigenvalue pairs, remember that this equation came from a times x is equal to lambda times x, right? That's our eigenvalue eigenvector pair definition. So this turns out this form is a nice way to find these eigenvalues. We've already seen how to find the eigenvectors if we already know the eigenvalues. That's just the solution to a homogeneous system. In this case, we can use this fact and the fact that we're looking for non-trivial solutions to this system by realizing that if we're going to have non-trivial solutions to this homogeneous system, it means that a minus lambda I will not be invertible. So that's our key insight there, right? So in other words, if this matrix has a non-zero solution to this homogeneous equation, then it's not an invertible matrix, right? So invertible matrices have only the zero solution to the homogeneous equation. So that's our key insight now, because what we can do is take the determinant of a minus lambda I, as we've done up here to form this characteristic polynomial, and when we set it equal to 0, well, we're setting the determinant of a minus lambda I to 0 in that case. And what we're looking for, remember, lambda is some unknown, right? We're just going to substitute lambda into this each time. We're going to solve for lambda to find the values of lambda that make this true. That will give us a comprehensive list of the lambdas or the eigenvalues of A. In other words, the values of lambda that satisfy this determinant equation, right? The determinant of a minus lambda I, or in other words, the characteristic polynomial is equal to 0. And again, that's because what we're looking for ultimately is non-trivial solutions, x, to this homogeneous equation. And the only way that we're going to have such things is that a minus lambda I has a 0 determinant. In other words, it's not invertible. So let's use this to find the eigenvalues of an example matrix. So find the characteristic equation and then all the eigenvalues. Oh, it even asks for eigenvectors of this matrix A. So getting started with this, we need to form the characteristic equation by writing this down. A minus lambda I, take the determinant of this matrix and set it equal to 0. Just scalar 0, right? Determinants are scalars. So minus lambda I for a 2 by 2, well, it's just, that's the matrix negative lambda 0, 0, negative lambda, reading it by rows. Now, if I'm subtracting that from A, or if I'm doing A minus lambda I, I'm just going to have 3 minus lambda I, negative 1 minus, 3 minus lambda and negative 1 minus lambda. I have zeros everywhere else in my identity matrix or in my lambda times I matrix, so nothing else has changed in my matrix A. So really, this is the standard practice. You just move down the main diagonal of the matrix and subtract lambda in all cases. Now we need to take the determinant of this matrix. And when we do so, we get these two products for the top left to bottom right diagonal. And then we get negative 1 times negative 5 with a negative parity, so we have minus 5. All this is set equal to 0, as this tells us to do, or reminds us to do. or multiply this out, and we get this expression, minus of 5, combine like terms to get this characteristic equation here. So we have our characteristic equation, and that settles one part of this problem, right? The first thing they asked for. And then we need to find the eigenvalues by solving for lambda. And that's just a matter of factoring this characteristic equation to get lambda minus 4 times lambda minus 2 equals 0. And that tells us that lambda is 2 or 4. So those are our two eigenvalues for this matrix. Lambda equals 2 or lambda equals 4. Now, the eigenvectors we have not done in this example, even though it asks for it. I'll leave that as an exercise, but remember that to find the eigenvectors, we go back to section 5.1 and realize, well, I take each of my eigenvalues. In the first case, we'll have lambda equals 2. I'll do a minus 2 lambda, or sorry, a minus 2I. So then I'll subtract 2 from 3, and I'll subtract 2 from negative 1, and I'll have a column of zeros, and I'll find the vector v, or the vector solution, call it v or whatever you like, to that homogeneous problem by row echelon or reduced echelon form. And for each of these eigenvalues, we should be able to find an eigenvector corresponding to it. So again, we did that at 5.1, so I'll leave that as a nice exercise. Okay, so we get to add yet another element or another entry or equivalence to the invertible matrix theorem. Right, so this is continued from, I believe, at least 2 sections prior to this that reiterates or adds to or appends these equivalences to the theorem. For our n by n matrix A is invertible if and only if, and here's our new equivalence, the number 0 is not an eigenvalue of A. It's pretty easy to see this. What I have below is essentially the proof, just without the formal language in it. But note this, A minus 0I. So this is our statement that 0 is an eigenvalue, right? Well, the only way it's going to be an eigenvalue is if the determinant of that matrix is equal to 0. Well, A minus 0I on the left-hand side, well, that's just A. We're taking the determinant of A and it needs to be 0. Well, the determinant of A is 0 if and only if A is not invertible. So what we have now is an equivalence. If 0 is an eigenvalue of A, then A must not be invertible. Right, so these are equivalent statements. So the contrapositive of that, if 0 is not an eigenvalue of A, then A is invertible. So there's our sketch of that proof there, and yet another piece of information for the invertible matrix there, another equivalence. So algebraic multiplicity of an eigenvalue for an n by n matrix A is the multiplicity of the eigenvalue as a root of the characteristic equation. So that sounds quite complicated, but if you remember algebraic multiplicity, possibly from maybe partial fraction decomposition, we might have talked about multiple copies of factors in a denominator. This is very similar to that. Maybe they weren't called that at the time, but nonetheless, they could be. It's an analogous concept. Let's have a look at the example. So we're given the eigenvalues for a 5 by 5, or the characteristic polynomial, rather, for a 5 by 5 matrix. So we have lambda to the 5th plus lambda to the 4th minus 6 lambda cubed. We're asked to find the eigenvalues and their multiplicities for this characteristic polynomial. That amounts to solving the characteristic equation. 0 equals the characteristic polynomial and solve from there. Factor out that common lambda cubed to the front. We have lambda squared plus lambda minus 6 as a trinomial to the right here. Then that is equal to factoring this quadratic as lambda minus 2 times lambda plus 3. We have expressions for 1, 2, 3 eigenvalues. This lambda cubed is equivalent to lambda minus 0 quantity cubed, right? So that lets us realize that lambda here, the lambda cubed, is the eigenvalue of 0, which, by the way, tells us that whatever this 5 by 5 matrix is, it's not invertible. It has 0 as an eigenvalue. And we also have lambda equals 2 and lambda equals negative 3 as solutions to the characteristic equation. So those are our eigenvalues for this given matrix from this characteristic polynomial. So what are the multiplicities? Well, lambda minus 0 has 3 multiples, right? It occurs 3 times algebraically. It's lambda minus 0 times lambda minus 0 times lambda minus 0 technically, right? So that's multiplicity 3. Lambda minus 2 has 1 occurrence. It has an understood 1 in its exponent, and same with lambda plus 3. So the multiplicities of lambda equals 2 and lambda equals negative 3 each is 1. So each of those two eigenvalues has multiplicity 1. Notice when you add all the multiplicities together, you get back 5, right? It matches both the degree and the size of the n by n matrix, or in this case, the 5 by 5 matrix. And that will always be the case. Another place you might have seen this would have been in a college algebra class when you were graphing polynomials. We looked oftentimes at the exponents, maybe we called them algebraic multiplicities there, and determined whether or not the polynomial crosses at this 0 or just touches the x-axis at this 0. So touch or bounce on the x-axis by odd or even exponents for these roots of this equation, polynomial, the roots of this polynomial. Okay, so algebraic multiplicity is that. And we have one last concept to introduce in this section and one theorem to accompany that. So we'll have, if we have two n by n matrices A and B, they're said to be similar if there exists an invertible matrix P that satisfies this relationship, or equivalently, if we multiply by P on the left and P inverse on the right on either side of this first equation, we'll get the second equation. So we can write this one way or the other. So this is this notion of similar matrices. So it seems it may be rather vague at first. Why would this be of any value to us? But it'll turn out that this is a pretty powerful technique for rewriting matrices in different forms and applications that ensue from there. So let's see our first fact about similar matrices. If n by n matrices A and B are similar, then they have the same characteristic polynomial and hence the same eigenvalues with the same multiplicities. So that's an interesting fact. Let's see where this comes from. Really, all we need to prove is that they have the same characteristic polynomial, right? Because if they both had, say, this polynomial as their characteristic polynomial, well, then they're both going to have the same eigenvalues and the same multiplicities to follow. So all we need to show is that they have the same characteristic polynomial. Now, to that end, we assume that A and B are similar, and as such, there exists P and P inverse, such that B is equal to P inverse times A times P. So now let's do minus lambda I on either side of this highlighted equation. Thus, we have B minus lambda I is equal to P inverse AP minus lambda I. I'll have a quick look at I. Remember that P inverse and P are inverses of each other. So P inverse times P is equal to I. And really, if we left an I in the middle of them, well, then we'd have to associate with one or the other. But remember, the identity matrix times another matrix is just equal to that matrix. So maybe I'll move this around to here, write this in this form. We'll have that. This is also part of it. So yeah, the identity matrix times P on the left or times P inverse on the right, either this pair or this multiplication will leave us with exactly this expression, and P inverse times P is equal to the identity matrix. So we rewrite lambda I here as this whole expression, P inverse IP. Okay, and the reason we do that is because now we're going to factor P inverse out on the left of either of these terms, out of this expression, and P will factor out from the right on either side of this expression, and we'll arrive at this expression here, A minus lambda I, with a P inverse on the left and a P on the right. We see that if we redistribute both of those multiples, we'll get the line above once again. So this allows us to now calculate the characteristic polynomial. Well, we could have done it before, but this is a good place to to calculate the characteristic polynomial for each of these things. So that's just simply the determinant of this matrix. So this will give me the characteristic polynomial of B. What does it give us on the right-hand side? Let's have a look. Right, whatever it is, it's equal to the characteristic polynomial of B. So let's see where we end up. Well, remember that the determinant of a product, we have 1, 2, and 3 products here. Well, we can split up the determinant of a product as the product of the determinants. So we do that twice. We have the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. Now, also recall this fact from a previous section. The determinant of P inverse is equal to 1 over the determinant of P. I think we proved that back in chapter 3, I believe. So if that's the case, 1 over determinant of P times the determinant of P is going to be equal to 1. And we're left with only A minus lambda I, the determinant of that matrix, on the right-hand side. And thus, in the end, this B minus lambda I determinant is equal to the A minus lambda I determinant. Well, that means that A and B have exactly the same characteristic polynomial, which means that A and B have the same eigenvalues with the same algebraic multiplicities for each eigenvalue because they have that same characteristic polynomial. So we'll use that fact to do some nice work with similar matrices in future sections. So that's it for section 5.2.